Hello, everyone. This is the homework video for homework 3. So let's start with problem 1. So a 5-digit palindrome is a positive integer with respective digits A, B, C, B, A, where A is non-zero. Let S be the sum of all of these palindromes. What is the sum of the digits of S? So we know that the sum of a set is equal to the number of elements elements times the average. So to calculate the elements, we just have to multiply the number of choices for A, B, and C. So A can be any number from 1 to 9, which is 9, and both B and C have 10 choices. So there are 900 elements. And then for the average, firstly, we are going to consider A, B, C, B, A, and then break it up. So it is equal to 10,001A plus 1,010B plus 100C. Yeah, so to find the average, we just find the average of each of these terms. So A can go from 1 to 9, so the average is 1 plus 9 over 2 equals 5. And then both B and C are from 0 to 9, so the average is 4.5. So after calculating this, we get 55,000. So multiplying these two numbers, we get 495 followed by 5 zeros. So the sum of the digits is equal to 18, so our answer is B. Okay, let's move on to problem 2. Okay, so for problem 2, we consider the set of all fractions x over y, where x and y are relatively prime positive integers. And then we have to see how many of these fractions have the property that if both the numerator and denominator are increased by 1, the value of the fraction is increased by 10%. So we have that 10% to more than any number. X is just x plus x over 10 is equal to 11 over 10x. So this problem means solving 11 over 10 x over y equals x plus 1 over y plus 1. So after multiplying these fractions and cross multiplying, we get that 11x times y plus 1 is equal to 10y x plus 1. So we'll expand this and then cancel out 10xy. So now we're going to use Simon's favorite factoring trick. So xy plus 11x minus 10 y minus 110 is equal to negative 110. So then we can just factor this as x minus 10 times y plus 11. So now we're just going to see what values that y plus 11 can be. So we're going to list out the factors of 110 that are greater than 11. We can see that they are 22, 55, and 110. So we're going to consider each of these cases. So if y plus 11 is 22, then x minus 10 equals to negative 5 because minus 5 times 22 is minus 110. So we have that y equals 11 and x equals to 5. So this works. The second case is y plus 11 equals 55 and x minus 10 is equal to minus 2. So we have y equals 44 and x equals 8. This doesn't work because they have a common factor of 4. And lastly, y plus 11 equals 110 and x minus 10 is equal to minus 1. So we have y is equal to 99 and x is equal to 9. This also doesn't work because they have a common factor of 9. So the only solution is y is 11 and x is 5. So the answer is B1. Okay, problem 3. So, how many ways are there to write 2016 as a sum of positive as a sum of 2 and 3s in ignoring order? So, 1008 twos and no threes, and 402 twos and 404 threes are two such ways. So, firstly, we are going to let there be x twos and y threes. Sorry. And so we have that 2x plus 3y is equal to 2016. So notice notice that we can now solve for x as 2016 minus 3y over 2. So we want this numerator to be a positive even number. So it's going to be positive if y is less than or equal to 2016 over 3, which is equal to 672. And it's going to be even if 3y is even or y is even. So so we're just counting the even numbers from 0 to 672. So 0 to dot 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 672. We can just half this list and add 1. We see that there are 337 elements. Let Sn equal the sum of the digits of the positive integer n. For example, S1507 equals 13. For a positive integer n, Sn equals 1274. Which of the following could be the value of Sn plus 1? So it is well known that Sn and n are going to have the same remainder when divided by 9. So what we so we know that n's remainder when divided by 9 is just the remainder of this divided by 9, which is just 5. So n has n has remainder 5 when divided by 9. So, well, that means that n plus 1 has remainder 6. So Sn plus 1 must also have remainder 6. 1 has remainder 1, 3 has remainder 3, 12 has remainder 3, and 1265 has remainder 5, so none of those work. The only remaining option is 1239, and we can see it has remainder 6. So let's move on to problem 5. How many three-digit numbers are not divisible by 5, have digits that sum to less than 20, and have the first digit equal to the third digit? So we can write this number as A, B, A, because the first digit equals to the third digit. So not divisible by 5. So A cannot equal to 5, and the digits sum to less than 20. So 2A plus B is less than no. 20. So now we're just going to consider the possible values of A and see how many values of B there can be. So A, 1, 2, 3, 4, 6, 7, 8, 9, and then possible values of B is going to be here. So if if A is equal to 1, then we have B is less than 18, so there's 10 values of B. If A is 2, then B is less than 16, 10 values. If A is 3, then B is fewer than 14, so there's 10 values. And if A is 4, then B is less than 12, 10 values. If A is 6, then B is less than 8. So there's only 8 values. If A is 7, then B is less than 6 values. If A is 8, then B must be less than 4, so there's 4 different values. And if B is if A equals to 9, then B is less than 2, so B can only attain 2 values. So adding all of this up, we just get 10, 10, 10, and 10, 10, which is 60. And problem 6, this one's a little harder. So there are no solutions to x squared plus y squared equals k squared and xy equals k. So this also means that there are no solutions to x squared plus y squared equals k squared and x squared y squared equals k squared. We see this is just the square of this equation. There can't be any solutions to this either. So we can let x squared be equal to t. Then we have that y squared is equal to k squared minus t. So there are no solutions to the equation t times k squared minus t equals k squared, where t is non-negative. So this means that there are no non-negative solutions to what? Negative t squared plus k squared t equals k squared. So just rearranging some stuff. T squared minus k squared t plus k squared is equal to 0. So there are no non-negative solutions to this. So we can so we get that the determinant must be less than 0. So the determinant is negative k squared minus 4k squared 1. So this is less than 0. It's easy to check that the only values of k for which this is true are 1 and negative 1. So checking that these original equations have no solutions is easy. So to show that these have no solutions, we have that x squared plus y squared equals 1, and xy equals to 1. And so if this had solutions, that would mean x squared minus 2xy plus y squared equals negative 1. But then x minus y squared equals negative 1, and that obviously isn't true. If we replace this with negative 1, then we have kind of the same story, but we just change some of the signs. So 1 and negative 1 are the solutions to this problem, and the answer is 2.